everyone. Welcome to day one of the Autodesk Advanced Manufacturing Summit. My name is Ann Polly, and today I'll be doing a session on how to effectively integrate additive manufacturing into your product development workflows. I'm a mechanical engineer on the design and engineering team at Fathom in Oakland, California. And my team works with clients to develop products all the way from concept to manufacturing. Working within Fathom, which is an advanced manufacturing company with both additive and traditional manufacturing, not only can we leverage all of those options that are available, but gain an insight into how most of our customers use these technologies most effectively. Starting off, I'd like to go through some of the processes that are most readily available to product designers, either through their in-house additive manufacturing services or through service bureaus like Fathom. Starting off, we'll discuss FDM, or fused deposition modeling. Now, this technology is usually most familiar to designers because of the availability of desktop FDM printers. Now, one of the advantages of FDM is the ability to print with some high-performance engineering plastics, such as nylon 12, carbon-filled nylon 12, polycarbonate Ultem, and PEC, in addition to ABS and ASA, which are the most common choices. FDM is also capable of printing larger parts than a lot of the other technologies, up to about 900 millimeters squared and 600 millimeters deep, which is about 3 feet squared. The surface finish on FDM parts is typically glossy, but has noticeable layer lines. And oftentimes the accuracy of the features on FDM parts are dependent on the orientation that the part is printed in. For example, you can see in the upper right image on the slide, a round hole that's printed in the vertical face of the part can sometimes have some distortion along the edges due to those layer lines, whereas the same hole, if printed on a horizontal surface, may not have that same distortion. Now, another advantage of FDM is that it typically has a very fast turnaround, which is very dependent on the part size, because typically FDM builds are done with either one part per build or small runs, such as what you see in the upper left image. Some of those high-performance plastics that FDM allows us to use are Ultem, PEC, and carbon-filled nylon 12. And Ultem is well known for its high temperature resistance, high chemical resistance, strength. It's also food safe and biocompatible. It's the only material that we offer that is certified food safe. PEC is also tough and has high heat and chemical resistance. It also offers very good wear resistance. Carbon-filled nylon 12, it's excellent for structural applications, and it has the highest stiffness to weight ratio of any of the FDM materials. SLA, or stereolithography, is usually the process that most people are familiar with in addition to FDM because of the availability of desktop SLA printers. Now, with industrial SLA printers, we're able to print much larger parts. And so SLA is often very, very cost efficient for medium to large parts because those parts can be printed on one build very quickly. With SLA, the materials that we have available are Accura 25, Accura Black, and Watershed. Accura 25 is the white material that you see in the images that has somewhat of a semi-gloss to gloss finish on it. And Watershed is a high clarity, clear material. The surface finish on SLA parts is usually around a gloss or a semi-gloss, and it has very subtle layer lines. Because of this nice smooth surface finish on SLA parts, one of the best applications that we use SLA for is prototyping and fit checking parts that are intended to move on to additive manufacturing. It's also a very good choice for testing assemblies before moving on to production. Next up, we have SLS, or selective laser sintering. This process uses a nylon powder bed and a laser to sinter the nylon powder together. And the materials that are available for SLS are nylon 12, nylon 11, and some variations on that, including glass bead, carbon filled for nylon 11, and a fire retardant material. Most of these parts come off the printer a bright white color, with the exception of carbon filled, which is gray, and glass bead, which is slightly off-white. SLS is also capable of medium to large parts up to 700 by 380 by 580 millimeters. However, it may not be quite as fast or as cost efficient for these large parts as SLA. The surface finish on SLS, because it's a powder bed process, has a consistent, fine-grained surface finish. And because SLS is sintered powder, the parts can be somewhat porous. A majority of the SLS materials come off the printer a bright white color. However, they're often dyed to a requested color. One important thing to keep in mind with SLS is because these parts are printed at a high temperature and then cooled, there is some potential for warping. And so parts that have large, flat surface areas with thin walls may see some warping and may not be the best fit for SLS. For parts that have flat, thin walls, we always recommend that ribs or gussets be incorporated, and holes on flat thin surfaces can benefit from bosses, which is very similar to part design for injection molding. Next up, MJF, or multi-jet fusion, has some similarities to SLS because it's also a nylon powder bed process. However, in contrast to SLS, instead of sintering the material with a laser, MJF uses a fusing agent combined with an infrared light source to create the parts. Now, the materials available for MJF parts are nylon 12 and nylon 11. Typically, we print most of our parts in nylon 12. However, for some applications that may require more flexible parts or higher impact resistance, we may use nylon 11 instead. MJF doesn't have quite the same build volume that we can achieve with SLS. It can print parts up to 274 by 370 by 360 millimeters. Because MJF parts are printed using a white nylon powder bed combined with a black fusing agent, the parts come off the printer with a gray color, which we often dye black in order to achieve a more even color and finish. Because these parts are a solid, consistent black material on the inside, when machined, the machine surfaces are a smooth, glossy black. And when gray parts have wear, it also begins to show more of that black interior. MJF parts have a relatively soft, fine-grained texture, and it's very similar to SLS with slightly narrower layer lines than SLS. However, we can tumble the parts to achieve a softer surface finish. Similar to SLS, since these parts are printed at a high temperature and then cooled, we do have to consider the potential for warping in the parts and design the parts accordingly. Polyjet is a really versatile technology because of the wide range of materials available, as well as the ability to print multi-material parts. All of the materials for Polyjet are photopolymers because the process prints using a print head and then curing with UV light. And the materials available include a wide variety of rigid materials, rubber-like materials, as well as both opaque and transparent materials, and even biocompatible materials. Polyjet also has the fastest turnaround time of any of the technologies because not only is the printing process very fast, but the builds are usually a single part or a small batch of parts. Polyjet has two basic surface finishes that are available, gloss and matte. However, the gloss finish can only be achieved on the top surface of a part because Polyjet does not have the ability to print overhangs without support, and any surface that has support material must be matte. And the result of this is that most of the parts that we print using Polyjet are printed with an entirely matte finish, which is what you can see on the sculptural model on the slide. One of the biggest advantages of Polyjet is the ability to print multi-material and full-color parts. So aesthetically, we're able to integrate both opaque and translucent materials as well as a full color spectrum. This is really advantageous for printing concept models, realistic full-colored prototype models, end-use medical models, such as the bottom image on the slide, as well as multi-material capabilities for mechanical properties, which allow us to print prototype parts for traditional manufacturing, such as overmolding, or achieving intermediary properties, such as intermediary durometers, which combine those rigid materials with rubber-like materials. DMLS, or direct metal laser sintering, allows us to print in a wide variety of metals and alloys, and the geometric freedom as compared to machined components allows a lot of interesting design choices, such as combining parts to reduce part count and integrating complex geometries such as lattices that are not possible using traditional manufacturing. This process is also very versatile for prototyping parts that are intended for traditional manufacturing because it eliminates the need for tooling. DMLS has a smaller build envelope than most of the other processes, with max dimensions of 11 by 11 by 13 inches. The surface finish on DMLS parts as printed is typically a rougher texture that's similar to the surface finish on a cast part. However, there are a wide variety of post-processing technologies available for DMLS parts. These parts can be machined in order to achieve a smooth, high-tolerance surface, such as in the upper right corner. It can also be tumbled, shot peened, and polished in order to achieve a better surface finish. Now, moving on to some applications for additive in product development. One huge advantage to additive is the ability to do a lot of iterations in order to test things like ergonomic features. One product development cycle where this was used very effectively was at the Nonfiction Design Studio in San Francisco, where they printed more than 700 parts in order to make fine adjustments to fit the ergonomics, as well as part fittings such as audio drivers and microphone positions. And this product was a really innovative headphone design that is an over-the-ear headphone that clips directly onto the user's ears. And so the ergonomic design for this product was extremely important, and additive manufacturing played a huge role in the viability of this design. Additive also has a lot of capabilities for aesthetic features. For clear parts, the options that we typically choose are either Polyjet or SLA. SLA, the watershed material, it has very high optical clarity. It does require polishing and clear coating to achieve that high clarity finish. Polyjet is also capable of printing very clear materials and can be polished and clear coated. It also offers us the capability to combine it with other materials such as opaque materials. Finally, the multi-material capability in Polyjet allows an entire range of clear and translucent materials where we can produce gradients of clear with opaque materials as well as different colored materials in full color Polyjet printing. Generatively designed parts are also an amazing fit for additive manufacturing. Most often, we use either SLS or MJF for generatively designed components because it's capable of achieving the complex organic geometries with consistent surface finish thanks to the self-supporting nature of the process. We're also able to print generatively designed components using Polyjet and SLA, but the structural properties may not be quite as good as the SLS and MJF nylon material. FDM is also capable of printing generatively designed components, but may suffer from layering or anisotropic properties. As many of you know, generative design only accounts for isotropic materials, and so this is an important consideration for whether or not FDM would be a good choice for the parts. FDM might be a good choice for generative components that are very large that would not be able to fit on one of the other printers. Model finishing is also a really great application of additive. This includes both finished one-off models and post-processing finished parts to achieve a certain aesthetic. Painting is a process that we do pretty often on additive parts, and polishing is common for SLA and Polyjet, which are the resin processes. Tumbling is common for MJF and SLS and DMLS. On MJF and SLS, tumbling gives the parts a much softer, finer appearance. And both of these processes can also be combined with either painting or dyeing for SLS and MJF. Finally, electroplating is also a possibility for additive parts, such as the part that you see in the bottom left image on the slide, but can often be cost prohibitive. Mechanical features are also a huge consideration when choosing which process is the best fit. For example, snap fits are a very common design element in prototyping. With snap fits, MJF and SLS are a really great fit because the nylon material creates good mechanical properties, and SLA and Polyjet can also be a good fit. It is important to keep in mind that depending on the material, some of the resin parts can be more brittle than nylon. However, Polyjet offers a wide range of intermediary materials, such as materials that simulate polypropylene. FDM can be used to print snap fits, but similar to generative design, the functionality of the part may be affected by layering and anisotropic mechanical properties. When printing snap fits with FDM, More flexible materials such as nylon are typically the best fit, and the print orientation of the part is very important to the functionality of the snap fit. For threaded holes and threaded inserts, this choice depends a lot on whether the fastener will be repeatedly screwed in and removed or will be inserted once. If the fastener is only going to be assembled once, then direct threading and tapping may be a good choice. However, if the screws or the fasteners will be removed repeatedly through the threaded hole, we recommend using inserts such as heat set inserts, self-tapping, or press fit inserts. Typically, heat set inserts are the best choice because they are difficult to remove from the part. They can take a much higher tensile load. However, heat set inserts are only able to be used in FDM, MJF, and SLS parts, because only thermoplastics can accept that heat set insert. Therefore, it's not possible to use heat set inserts in SLA and Polyjet parts. However, self-tapping and press fit inserts could be a good choice for any material. It's important to consider with self-tapping inserts as well as directly inserting fasteners in parts that brittle materials might be more prone to cracking. Elastomers are also something that we have access to with additive manufacturing. FDM, Polyjet, and powder bed processes are all capable of printing using elastomer materials. However, there are distinct advantages and disadvantages of each. For example, if I'm printing a medium to larger part that is all one material, if it's all TPU, I would likely choose FDM. If I am looking for more consistent properties, or I want to print a multi-material part that includes an elastomer, I would choose Polyjet. Now, Polyjet's very versatile for things like gaskets, as well as prototyping overmolded components. Finally, powder bed TPU is also a material that's becoming more and more available recently. It's becoming available for both SLS and MJF. Now, powder bed, similar to nylon, there is some porosity in those parts. And so the applications that we see the powder bed TPU being used for are things like lattices, where the self-supporting printing process has a lot of advantages. Moving on, I'd like to discuss a little bit about additive manufacturing as a production technology and where it might be a viable choice over traditional manufacturing. One application that we've seen in very recent history is stopgap manufacturing using additive, such as with COVID-19 testing swabs. Now, in this project, we collaborated with our colleagues at HP and Abiogenics, as well as medical professionals from Stanford and Harvard, in order to develop a nasal swab that is intended for additive manufacturing. Using the additive technology from beginning of design to production was only a 35-day cycle. For manufacturing, we produced swabs using MJF nylon 11, and we were also able to achieve FDA approval and high QC standards for these parts, as well as securing sanitizing and medical packaging. Lattices and foams are also a really interesting application for additive that we're seeing used more and more. Now, in contrast to traditionally manufactured foams, additively manufactured foams can have variable properties across the entire structure. So some interesting examples where we've seen this used are the Hexa surfboards, which substituted a traditional foam core surfboard for an additively manufactured lattice, which was printed using bioplastic. Not only were the materials for this process more environmentally friendly, but the process was more efficient and used less energy. We're also seeing the variable lattice structures used a lot in applications such as footwear, where we may want a more customized part, or we may want a structure that has different properties in different locations. One project where we saw additive for bridge production used very effectively was the V-Arcade project. Now, in this project, additive was an obvious choice for prototyping the design, which was a wireless VR headset that was launched in Dave & Buster's locations. However, FDM turned into a really advantageous bridge production technology because the product launch was only 20 units. And so between additive and injection molding, there was a difference of $250 versus $800 cost per part for that quantity. Using additive, it was also possible to combine the parts from 4 down to 2. Small runs is also an excellent application for additive manufacturing, such as the small run with the V-Arcade project. Another project where small run additive manufacturing was used effectively is a project that we did with Mercedes that you can see in the upper left corner, where we were creating a small run of 40 parts. And these parts were done using SLS, which was not only more cost effective for that quantity, but it allowed us to identify room for improvement in those parts before moving on to a higher quantity. Finally, customization is a really great application for additive manufacturing, such as the customized fitted arm brace or custom shoe insoles that can be made using a person's individual use data. Thank you, everyone, for coming to my session on additive manufacturing and product design. Please feel free to reach out to me or Fathom at any point if you would like to discuss more about additive and the product design workflows that you're working with.